Hello, good evening. Today is December 17th, around 10:30 p.m. Dallas time, which is US Central Standard Time. And I'm making this recorded presentation, a video presentation of a talk I gave about a year ago in Kona, in Hawaii, when I received the award from IEEE Comsoc Communications Society at the GLOBECOM Conference, IEEE GLOBECOM Conference. And this award was given to me. It was a technical recognition award in computer and information security. So it is an annual award. I believe it's it's communication security, right? So it's an annual award that is given. So I was very honored to receive this award at the special awards meeting. And at this award ceremony, I also had to give a short talk, about 20 to 25-minute talk on my research. I got this award for my research on applying data mining for network security. And I've been doing work on data mining for cybersecurity in general, network security in particular, since around 1995-96. And more recently, over the last 15 years, I've done a lot of work with my colleagues and students on applying data, not only data mining, it's sort of gone to data science, as well as big data techniques for cybersecurity. So I'm going to give a short overview of what I have done in this area. Okay, so I'm going to share my screen. Let's see. Share screen. So I've got it all set. Let's see. Where is oh yeah, it's here. Okay, so data mining, data science for network security problems. And this presentation was given, as you can see, December 11th, 2019. It was presented at the IEEE Technical Committee meeting on Communications and Information Security at IEEE GLOBECOM 2009. And this was the award I received on Communications and Information Security, right? That's the exact wording. Okay, and it was a technical recognition award. And I was most honored to receive this award. And this was about a year ago. And one thing to mention though, when I got this award, we're all in Hawaii. And who would have thought that 1 year later, we would be, behind sort of closed doors, meaning that we'll all be at home working and I'll be making this virtual presentation. Anyway, hopefully next year we can have, at this time, we can have face-to-face meeting at GLOBECOM again, and that will be 2021. Okay, so my work in communication networks and data mining, data science for network security, okay? So I started my career actually in network design and development at Control Data Corporation. So CDC-net, Control Data Communication Network, that was one of the early communication systems, networking system products that was developed for control data mainframes, Cyber 170 to connect to various terminals in schools, as well as to connect to applications and connect to Cyber 180 family of products. And so I did this work from fall of 1983 to January 1986, and we completed the first release in December 1985. And so 1986 January is when I joined Honeywell, but I got into cyber security, actually network security, in the fall of 1985 in preparation for my interview at Honeywell, as well as hoping that I would get my job at Honeywell to get to work in computer security. Anyway, so when I was at Honeywell, I designed one of the projects. My main project was to design one of the early high assurance secure database systems. But while I was there, part of my work was also on the design and development of a network operating system for space stations. And that work was done for NASA, National Aeronautic and Space Administration. So we had to integrate networks, right? Build a local area network as well as integrate multiple networks at space stations. So that was at Honeywell. And then at MITRE, I did a lot of work on integrating real-time systems and security for next generation AWACS, that is Airborne Warning and Control System. And that was from 1993 to 1999. But throughout my career, from 1985 to about 99, even today, much of my work is in data and application security and privacy. But this particular award was for my work on data science for network security. So while I was at NSF, while my main efforts were on information and data management and data and application security, I also contributed to various initiatives in sensor networks, managed programs, in particular sensor networks as it relates to information management and information technology research at the National Science Foundation, in particular information technology as it relates to information management. More recently, at the University of Texas, Dallas, my work includes data mining for network security problems such as intrusion detection, a lot of work 2005 to 10, assured cloud-based information sharing. How do you share information in a cloud securely? And that's from 2018 to 14. Privacy-aware quantified self, a lot of work on how to ensure privacy, policy-based privacy-aware framework. Quantified self movement is the movement by sociologists and psychologists to help us to lead better and healthier lives. But that means a lot of data has to be collected about us, which means that we need to ensure privacy. So that's 2015 until now. And data science for insider threat detection between 2010 to 2015. And adversarial machine learning. What happens when the data science and machine learning techniques are attacked? That would be devastating, right? So that's the current work and one of the most popular areas in cybersecurity. And integrating AI, cybersecurity, and the Internet of Transportation systems. And that's 2017 to present. So this is sort of summarizes not all of my work, just a part of my work that applies data science for network security. So here is one project where this was early work between 2005 to 2010, and that is data mining for intrusion detection in hosts and networks. So we looked at support vector machine, and support vector machine trains classes, right? So we do training and testing, and if it's a good class, that means it's good, it's not a malware or it's not an intrusion. If it's bad, then it is an intrusion. So we looked at traditional support vector machine, we did some testing training, looked at accuracy, false positives, false negatives, and then we came up with a highly novel technique called hierarchical clustering, DGSOT, dynamically growing self-organizing tree. Because if you do support vector machine, you can go on and on and on and start learning, and it can take a very long time. So DGSOT, right, a novel DGSOT algorithm integrated with support vector machine, it knows exactly when to stop, right? At the right point, we need to stop. That's a challenge. And so that's what we did. And we got some very good results, significant improvement over traditional support vector machines. So that was sort of my one project. Then we looked at integrating secure cloud with policy-based assured information sharing. So what did we do here? So we built our secure cloud, which is based on Hadoop MapReduce, and then we built a policy layer. So our policy layer was based on RDF, that is the resource description framework, right? Semantic web. Sir Tim Berners-Lee's semantic web, that's the next generation web. So we use the technology to develop this resource description framework-based policy layer. And then you have multiple agencies, agency 1, 2, and 3, and they are sharing all of their data and policies in the cloud. So they just sort of dump their data and policies. So when agency 1 wants to get data from agency 2, some information, agency 2, the policies could say, should ask agency 2 to ask agency 1, why do you need this data? Or I can give you this information provided you give me some other information. Or it can say, I can give you this information provided you don't share this information with agency 3 or 4 or N. So we demonstrated this with UT Dallas Agency 1 and King's College London Agency 2 and University of Insubria, Italy Agency 3. And we demonstrated information sharing. So this was one of the early cloud-based information sharing. And what we didn't do is we could go, some of the research, we also looked at encrypted data, right? Because if you put our data in the cloud, if it's not a private cloud, if it can be accessed by the public, then there is no security. So hopefully, eventually the technology, we have done bits and pieces where we encrypt the data, store the data, and then we query and share the encrypted data. Okay, so that part was sort of some research. And also we said, we looked at hybrid clouds, which data to go into private cloud, which data into public cloud. So it was some very useful work, some of the early work for assured information sharing. So that was, I look at it, one aspect of data science, integrating data science and cybersecurity/network security. Okay, so another thing we said was the quantified self movement. That's what the sociologists and psychologists, right? They really want to help us, right, to have a better life. So collecting healthcare, fitness, location, social media, image, and so on, stored in our smartphone. Wouldn't it be great if all of this information can be collected and a refrigerator from our smartphone and sent to our refrigerator when I open the refrigerator, because I love vanilla ice cream and chocolates. So when I open the refrigerator and start eating those chocolates or the vanilla ice cream, it will say, no, you cannot do that, right? But by privacy, all this information is being collected. That information could be sent to my insurance company, and the insurance company could deny me coverage because they say, oh, she's going to eat chocolates. Then there's a potential for her to have diabetes in the future, right? So that's the challenge, right? So some data, of course, because we can't store all of the data here. So some data goes into cloud, and then we can also get some services from the cloud. So what we are designing and developing, privacy-aware quantified self-manager running on the mobile device. But what is the challenge? Policies have to drive the entire process. Policies have to specify how to collect the data, saying that, for example, certain data can be collected, but certain other data cannot be collected. You can only collect the data provided you inform the user, get informed consent, data storage and access, data analytics, data sharing. Okay, so that's the policy-based, privacy-aware, quantified self. Okay, so that's a very interesting project. Okay, so another project, and I'm just talking briefly. So this is what I mentioned, what I discussed when I received the award. So you have to understand I was given, I think, at most half an hour to give this presentation. And so I'm just talking about some of the key areas. So I've talked about data mining for network security, intrusion detection. Then I talked about assured information sharing in the cloud. Then I talked about privacy-aware policy-based data management framework. And now we have data science for cybersecurity applications, and in particular, big data stream classification, right? So what happens? We use past data to build classification model, predict the labels of future instances using the model, and it helps with the decision making, right? So you get lots of network traffic, and then you have the firewall, and then you have the classification. Previously, like 20 years ago, we only built one model. But before I come to this picture, so we have data streams. Data is continuously arriving. Financial data, network security data, right? And they're very common in our digital world, and massive amounts of data. So the concepts could be changing, meaning that today it could be by Microsoft, tomorrow it's going to be by Oracle, another day by Google, another day by Amazon, and then Facebook. So one model is not sufficient. We built an ensemble of models, but then these models could grow infinitely large, right? And so our ensemble of models, once the models are not become sort of outdated, we throw away the models. And how do we throw away? All of these models have to work together, and perhaps with some human expert analysis, and throw away the models that are outdated and work with the models that you have. When test data comes in, you have the attack traffic, right? Block and quarantine, benign traffic, goes into a server. And we apply this to what? Inside a threat, another application. And that typically happens in networks and systems and so on. So insider threat means bad people pretending to be good people in an organization. This could also happen to processes, bad processes, and these processes could be, just some very, looks to you, it'll look like some very legitimate application, right? But they are pretending to be good processes. So we collect a lot of the data, system calls, chunks, we gather data, feature extraction. We have done unsupervised as well as supervised. Supervised algorithm support vector machine. A special type of support vector machine is one class support vector machine. And our unsupervised is graph-based anomaly detection. And then we build these ensemble of models, and the models get updated from time to time, right, when the concepts are changed. And then the I+1 chunk comes in, and feature extraction and so on, do testing. And if it's anomaly, of course, you will block and quarantine or carry out further investigation. Right. So this was one of the applications. So that is data science for cybersecurity. Now we come to the most interesting, dangerous part. What happens if the cybersecurity techniques, the machine learning techniques are attacked? We are applying machine learning for everything almost, right? Whether it's healthcare or COVID-19 or financial markets or retail or marketing, you name it, we are applying AI machine learning. What happens if the drug discovery, what happens if these machine learning techniques are attacked? We won't be able to depend on this machine learning, right? It can say buy Amazon, right? Why they should really be saying buy Facebook. You see what I mean? So, or it can say that you have a disease, you could have, say, you are having, it's just some indigestion, but in reality, you could be really having a heart attack, right? So the adversary is modifying data to defeat the learning algorithms, and you've got to understand the adversary, learn about the adversary. The adversary is learning. It's not concept drift, not what I mentioned earlier. It's not online learning. Adversaries adapting to avoid being detected. It could happen during training time, poisoning, and during testing time, modifying features when data mining is deployed. So there's a game being played between us and the adversary. So see what happens. The red squares are bad instances and the blue circles are good instances. And this is the support vector machine boundary. See what happens. What the bad guys are trying to do is to push the bad instances below the boundary so they will not be caught. So we can't let this happen. So we've got to learn what the adversary is doing, and using some mathematical computations, we have shifted the original support vector machine boundary to this blue line. So black dashed line is a standard support vector machine boundary, and the blue line is the adversarial support vector machine classification boundary. And so by shifting it, some of the bad instances are now being caught. Right, so here it's more clearly explained. So bad instances are red squares and the black squares. So you can see a lot of the black squares are being caught. So the question you can ask, green circles are good instances. Okay, we might as well move this right here so we can catch all the bad instances. No, if you move this right back here, up here, then the green circles here would show as bad instances. But no, we do not want false positives, but we do not want false negatives. So our challenge is to come up with a lot of mathematical computations and push this dashed line to this blue line. So that's the challenge. So this was one of the early works on adversarial machine learning. And since then, we've done quite a bit of work, and others have also done a lot of work in this area. Okay. So now we come to another type of network. Internet of Things, networks of networks of networks, connecting our cell phones, our smartphones, to the refrigerator, to the radio, to the television, to our computers, and then all our healthcare stuff, our Fitbits are all, and with the glucose monitoring, our heartbeat monitoring, whatever, everything is connected to our blood glucose levels, to our healthcare records, okay? And then comes all the financial stuff is connected, so Internet of Medical Things, Internet of Financial stuff. And now all our transportation systems are connected. So look at this, all the cars are connected to trains and to trucks and to this road building. So this is very important. We need this, right? For us to have reduced driving, for us to be safe, right? Because, we know exactly the routes to take. If we take the wrong route, they'll tell us exactly where to go. So this is very important. But these systems could be attacked. Imagine what happens if they are attacked, right? In the middle of somewhere that takes you to some remote location, and somebody can lure you there and then kill you. So we have developed a physics-based anomaly detection. That means we take the physical properties of the model, of the car. So the vehicles, so autonomous vehicles, right? So these vehicles could be aerial vehicles, it could be land vehicles, it could be sea vehicles, but we did only for aerial, drones, and for cars. So we looked at the physical properties like the moments of inertia and the mass and the velocity, and look at all the equations what control system theorists do. So we built a model offline of the AV physical invariants, the physical model, and then we built an online tool to monitor expected and observed behavior to detect anomalies. This online tool is the tool that we call, that used extended Kalman filters. So we didn't do any fancy machine learning. Kalman filters have been around for a long time, and physicists and especially control theorists, electrical engineers have used that. And then we raise an alarm using an algorithm called CUSUM, C-U-S-U-M, if significant residual difference exists between the executions. So offline pre-processing, online verification, anomaly detection. And so this was the work, again, with my colleagues. Everything is, this is with Alvaro Cardenas, professor, and our joint student, Dr. now graduated PhD student, Dr. Raul Quinones. Okay, so my last chart, right, because we've done, again, I'm only giving you a sample, exactly what I presented at the award ceremony. And that was, as I said, 1 year ago. So the next steps, developments in integrating cybersecurity and AI, right? Data science, machine learning exploding. So how can we bring, right, to integrate the two? Application of AI for security in cyber threat detection and security for AI adversarial machine learning. We also talked about developments in privacy-aware healthcare and managing one's life's activities. So privacy-aware quantified self. So policies have to guide the entire process. At the same time, with the development of Internet of Things, including Internet of Transportation Systems and Infrastructures, right? Security and privacy solutions are being developed, mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI ML techniques, right? Because that is, because if it's driverless cars, right, you need AI ML to direct those cars. But what happens if these AI ML techniques are attacked? How can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work in AV systems? And the other question, can we develop a privacy-aware policy-based data management framework for Internet of Transportation? So just like I showed you earlier with our smartphone, collecting all the data and doing analytics. So in my detailed presentation on this, we have a car. Inside the car, we have this sort of a gadget, which is collecting GPS data, LIDAR, radar, all kinds of data, and then analyzing the data and using the data. So the data collection has to be according to policies. And then, okay, so is it possible to perform trustworthy analytics? Remember, Intel has come up with the SGX platform to carry out trustworthy analytics, secure analytics. So what happens here is that you have different, the platform is in such that highly security critical functions can be executed in security critical, secure hardware. Okay, but there are some issues here where Intel SGX platform, there is some articles recently that they could be vulnerable. So we need to look into this more. So can we bring that trustworthy analytics, right? Analytics is being carried out in a trustworthy enclave is what Intel calls it. Again, numerous opportunities exist for substantial research. So I've only, it's sort of scratched the surface here, right? Each one of the charts I've shown you, I can elaborate that into a presentation, right? But again, the whole idea was to talk about my work. I was asked to present my work. And so I'm going to stop sharing. and then sort of end with some key points here. So as I said, right, data science for cybersecurity, or data mining for cybersecurity, network security. We have been working on that, and the community, for about 25 years. About 93, 94 is when it started. And then data mining exploded in the late 1990s, and there was all these discussions about privacy. And so by 2005, we were looking at more machine learning. And then by 2010 came data science, and then beyond that came AI. So I look at AI, data science, data mining, machine learning, all of that, to put it into one jar, or one pile. The other pile is all of the cybersecurity problems, right? So AI applied for cybersecurity, yes. And cybersecurity applied for AI, because AI techniques could be attacked. So that's a big concern that we have. But then throughout, we've got to be concerned. We cannot forget about privacy, right? And so as the systems become more complex, right, from Internet of Things to Internet of Transportation and Internet of Transportation could just not be only ground, as I said, ground, sea, air, and they all could be connected, because especially, say, when you want to coordinate, right, all the activities of the airplanes and the ships and the ground vehicles, all of them have to coordinate, then they all have to be tightly integrated. So that's, again, going to be the future. But imagine the amounts of data being collected, and how much privacy could be violated, and how the data could be attacked. And so that's why we need to bring in security, privacy, AI, all of that together. And we need to provide integrated solutions. We are not living in a perfect world. So we have to make trade-offs. In some situations, we have to be concerned about security, and some other situations, privacy could be very important. So I hope that gives you, I think I've talked for about 20, 25 minutes. I hope that gives you a flavor of some of the things that we've been doing. And I'm going to put this presentation on my YouTube channel. And so, so that you can look at my YouTube channel, lots of presentations. Some of the charts I mentioned here, of course, I've got several presentations based on those charts. So there could be some repetitions, but I try to present them under different scenarios, right? So you can see why they are being applied. Like last week, I gave a keynote address on December 10th at Big Cyber. So I was talking about terrorism and COVID, right? How do we compare the two? Okay, some of the things I mentioned in 2001, 2002, are they valid now, 2020, 2021? So those are some of the things that I've been discussing throughout my presentations. And so I'm going to continue, as long as you're working from home, I'm going to continue making these presentations as I give keynote addresses. I've given about 17 keynote addresses and about 11 panels while staying at home and working from home. But I'm also taking some of the important presentations I gave before March 2020, not everything, some key presentations, and I'm also recording them and posting them, uploading them on YouTube. And again, thank you very much for listening to this presentation. And again, today is December 17th, 2020, and my presentation was given at the IEEE Comsoc, IEEE GLOBECOM Conference, part of the Comsoc Technical Committee, Communications Society Technical Committee. It was the award technical committee meeting at the conference, and also receiving the award. So this was my award presentation. Again, thank you very much.